So far in this program, we've looked at transformers, voltage regulators, and capacitors, some of the individual components that make a distribution system work. In this part of the program, we'll turn our attention to the distribution lines that link the substation to the consumer and provide a path through which electricity passes. In a typical system, transmission lines run to a substation, supplying electricity at a transmission voltage. Inside the substation, the transmission lines are connected to the primary side of a substation transformer. The substation transformer steps down the transmission voltage to a distribution voltage. The secondary side of the substation transformer is connected to a substation bus. The substation bus supplies distribution voltage to distribution feeders. A feeder is made up of a number of wires that carry electrical energy at primary distribution voltage from the substation into a service area. In most systems, primary distribution voltage originates as three-phase power. Feeders, sometimes called primary mains or mains, consist of three individual wires that are buried in the ground or strung overhead on utility poles. Each one of these wires carries one phase of a three-phase feeder. Depending on the type of system that a company uses, a fourth wire, called a neutral, may also be part of the primary feeder. In this example, the neutral wire is located at a lower point on the pole than the three-phase wires. In the simplest of distribution systems, a customer is supplied with electricity from a distribution transformer connected to a feeder. The transformer receives electricity at a primary distribution voltage through a wire tapped off of a feeder. The transformer steps down the primary voltage to a secondary or utilization voltage, which a customer can use. Wires passing through the bushings on the secondary side of the distribution transformer form a secondary bus, which supplies secondary voltage to a consumer by way of a service drop. Distribution systems must be extremely flexible in order to supply various types of customers in a variety of geographic locations with electricity. A distribution system gets its flexibility from the number of ways that it can be laid out. In order to look at some of the different layouts, we'll use a simplified diagram of the system we just discussed. This simplified diagram represents a portion of a distribution system that supplies a service area. Here is the transmission line coming into the substation. Here's the substation transformer and the substation bus. These solid lines are three individual three-phase feeders. To keep our diagram simple, we're showing each feeder as a solid line. But keep in mind that each feeder is normally made up of three individual phase wires plus a neutral. Now, this substation supplies electricity to all of the customers within this service area. Typically, these customers include residential communities, industrial facilities, and office buildings located in various regions of the service area, which can be several miles apart. To reach customers in specific regions of a service area, laterals are tapped off the feeder. Laterals are nothing more than extensions of feeders that supply electricity at primary distribution voltage to regions of the service area that are not adjacent to the feeder. Connected to the laterals are distribution transformers with service drops supplying customers with electricity. In this simplified diagram, we're only showing one transformer on each lateral. In an actual system where the laterals extend for several miles, there may be numerous transformers on each lateral, as well as on the primary feeder. This type of layout is called a radial because the laterals radiate from the feeder to specific regions of the service area. Other layouts are also used. These include the loop and the duplicate supply. In a loop design, the lateral coming off the feeder runs through a region of the service area and has the capability of rejoining the feeder farther down the line. This is very common in residential communities that are supplied by underground systems. The lateral is connected to the feeder at one end by a fuse. At the other end of the lateral, there is also a fuse. This connection is often left open. With this type of layout, power can be supplied from either direction, depending on which fuse is opened and which fuse is closed. Loop systems are very flexible, and they provide a good deal of protection against long outages. If there's a problem on the lateral, service can be restored to the majority of customers on the loop simply by connecting the open fuse and disconnecting the closed fuse. The final type of layout we'll discuss is a duplicate supply, sometimes called a spot network. This type of layout is often used to supply hospitals and other urgent need customers who cannot tolerate a loss of service. A duplicate supply system is supplied by two separate feeders. It works like this. Taps from two feeders run to separate distribution transformers. One transformer is connected to one feeder, and the other transformer is connected to a second feeder. The secondary side of each transformer is connected to a secondary bus. From the bus, a service drop supplies electricity to the customer, in this case a hospital. Between the bus and each transformer is a protective relay. Under normal circumstances, both relays are closed. The secondary bus is then supplied with electricity from both feeders. However, if a problem develops, for example, with this feeder, this relay will open automatically. The bus is now being supplied from the feeder connected to this transformer. Even when there is a problem with the system, the hospital will experience no loss in service. As we indicated earlier, there are many different ways to lay out a distribution system. However, in most cases, the layouts will be variations on the radial, the loop, or the duplicate supply that we've shown you here. In this part of the program, we've identified three types of distribution lines: the feeder, the lateral, and the service drop. We've explained the type of voltage each line carries, and we've shown you three types of distribution layouts. Regardless of how a distribution system is designed, the lines and components must be protected from damage due to faults and voltage surges. The customer must also be protected from outages. We'll take a closer look at protection and protective devices when this program continues. The job of a power company is to provide its customers with a reliable source of electricity. In order to accomplish this task, a number of protective devices are used on distribution systems to protect the system and equipment from damage and customers from an interruption in service. What we're going to do in the last two parts of this program is to give you a basic overview of some of the protective devices used on distribution systems and give you a general explanation of how a coordinated protective system works. We'll begin by looking at two protective devices that are found in most distribution systems: circuit breakers and fuses. A circuit breaker is essentially nothing more than a large switch that can interrupt current flow through a line. When the circuit breaker is closed, the lines attached to the circuit breaker are energized. When the switch is open, the lines are de-energized. For the most part, circuit breakers are located inside substations. As you'll recall from the last part of this program, transmission lines supply a substation with electricity. The transmission voltage is changed to distribution voltage by substation transformers that supply electricity to a substation bus. The substation bus then supplies electricity at primary distribution voltage to feeders. In many systems, circuit breakers are installed between the substation bus and the individual feeders. Generally, there is one circuit breaker for each feeder. Let's take a look at a simplified drawing of a distribution system to see how circuit breakers fit into the scheme of things. On this drawing, we have a transmission line, a substation transformer, the substation bus, 3 circuit breakers, and 3 feeders. Again, for simplicity, we're showing the feeders as solid lines. In reality, the feeder is normally composed of 3 phase wires and a neutral. Most circuit breakers have indication of when the breaker is open and when it is closed. For our purposes, we'll use red to indicate that the circuit breaker is closed and the feeder is energized, and green to indicate that the breaker is open and the feeder is de-energized. The basic purpose of a circuit breaker is to protect its associated feeder from damage due to faults. Now, there are a number of different types of faults. For our explanation, we'll consider only a ground fault. A ground fault is a current flow path to ground that is not a normal part of a system's design. For example, under certain conditions, a tree branch coming in contact with a distribution line can cause current flow to ground. A malfunctioning component on a utility pole can also cause a ground fault. We'll return to our drawing and see what happens when a fault occurs on a feeder. Now, keep in mind that we've slowed down the sequence of events for our explanation. In reality, protective devices are designed to respond very rapidly in order to protect the system. At this moment, the distribution system is operating normally. All circuit breakers are closed and all feeders are energized. Let's suppose that a tree branch sways against this feeder, causing a ground fault. When a ground fault occurs, the current carried by the feeder has a flow path to ground that is not a normal part of the system's design. In most cases, this causes the circuit breaker to open, momentarily de-energizing the feeder. The other feeders and circuit breakers in the system will be unaffected by this action. In general, circuit breakers are designed to open and then close automatically after a specific period of time has elapsed. If the fault is temporary, as in the case of a tree branch swaying into a feeder, it usually clears fairly quickly. When the circuit breaker closes, service is restored, and the system continues to operate normally. However, if the fault does not clear, the current carried by the feeder will continue to flow to ground. This will cause the circuit breaker to open again for a period of time and then close. In some systems, this pattern of opening and closing will continue until the fault is cleared. In most systems, however, the circuit breaker is designed to open and close a set number of times and then lock out. That is, remain open until it is reset manually. Circuit breakers provide excellent protection against damage due to faults on feeders. Circuit breakers can also protect laterals that are tapped off of feeders. However, in many systems, fuses are installed between the feeder and the laterals to provide additional protection. In this example, the feeder supplies a 3-phase lateral and a single-phase lateral. This is what a typical fuse looks like. It consists of 2 contacts, one tapped off a feeder and the other connected to a lateral, and a hinged fuse. In the closed position, The fuse provides a flow path for electricity at a primary distribution voltage to flow from the feeder to the lateral. In the open position, the fuse separates from this contact and swings down, interrupting the flow of electricity to the lateral. Unlike circuit breakers that can open and close automatically, a fuse is designed to open and remain open whenever the value of the current carried by it exceeds its designed capacity. In most distribution systems, circuit breakers and fuses are designed to work in a coordinated manner for system protection. We'll use a simplified drawing of a feeder with fused laterals to see how this coordinated effort is achieved. In this drawing, we have a circuit breaker connected to a feeder with 3 laterals. The laterals are supplying electricity to residential communities, office buildings, and industrial facilities. At present, the circuit breaker and fuses are closed, and both the feeder and the laterals are energized. If a fault occurs on the feeder, the circuit breaker will sense the fault and open, momentarily de-energizing the feeder and the laterals. If the fault clears, service will be restored when the circuit breaker again closes. The fuses will not be affected in any way. However, if a fault occurs on one of the laterals, slightly different events take place. When the fault first occurs, the circuit breaker will sense it and open. If the fault clears, service will return to normal when the breaker automatically closes. However, if the fault remains, the circuit breaker automatically shifts to a different mode of operation. The second time the circuit breaker senses the fault, it delays opening for a short period of time. The actual amount of delay varies from system to system. Regardless of the system, however, the delay provides enough time for the fuse connecting the lateral to the feeder to open. When the fuse opens, the faulted lateral is isolated from the distribution system. The circuit breaker will then open and close. When the breaker closes, service will be restored to all parts of the system except the faulted lateral. This process is known as sectionalizing, and it provides protection to the distribution system and its components against damage due to faults. It also protects the majority of customers serviced by the system against outages. Circuit breakers and fuses are just 2 of the many protected devices used in distribution systems. In the next part of the program, we'll look at some other types of protected devices. But before we leave the topic of circuit breakers and fuses, let's review some of the points we've covered. We said that circuit breakers are basically automatic switches that can interrupt the flow of electricity through a distribution feeder. Circuit breakers have the capability of opening and closing automatically, and when used as part of a coordinated protection system, they can operate in a number of different modes. Fuses are used to connect laterals and feeders. A fuse can interrupt the flow of electricity through a line, but in most cases cannot automatically close to restore service. In a coordinated system, circuit breakers protect feeders from damage due to faults, and fuses protect laterals from damage due to faults in a process known as sectionalizing. Sectionalizing is simply the ability of a power company to isolate a part of a system that is faulted while continuing to provide service to the majority of its customers. We'll stop so that you can review the material in your text on circuit breakers and fuses and sectionalizing. And when we come back, we'll look at some other protective devices.